Hello, Maurieo. In this video we're going to be looking at calculating the area of the following shape. It's quite a regular shape, and we can see that it's readily subdivided into a number of different shapes, and I'll come to that a bit later on as to how we're going to do it. There are many ways that we could work out the area of this particular shape. First, I should point out that I'm working in a CAD program here. So I have drawn this shape to scale and used the dimensioning aspects of it to get the correct dimensions. And then I'm going to go through the calculation, and once I've done the calculation, check the calculation against the CAD values that I have. So let's just have a quick look at the calculation itself. These are, or the diagram, these are indicating right angles. Just note that these two sides are the same length, so this is what we would call an isosceles triangle. So we could, if we wanted to, calculate these angles here, and they should be equal. We've named the triangle A, B, C, D, E, F, and we've got a little B here that's unnecessary, so I'm just going to delete that, and there it is. And then we've got some little construction lines here, this one across here, indicating that this is a right angle, and that and again this here is a right angle. So I can see a number of ways that I could calculate the area of this, but I'm going to try and do what I think is the optimal way of calculating it. Okay, now I've turned on my construction layer where I have revealed my plot as to how I am proposing to calculate this area. The magenta line from F through to H then subdivides the area into three known shapes that we can calculate. First of all, we've got the rectangle ABHF, that we can calculate that area. We can then add the area of the trapezium FHDE. A trapezium is a shape with two parallel sides, in this case here FH and ED. And then we can add to that the area of triangle BCD. So first up, the area of angle ABHF, area of a rectangle, length times width, in this case 126.56 times 22.56 equals 285.19. So quite simple to verify that. Now let's have a look at the trapezium. The area of a trapezium is half the sum of the parallel sides times the distance between them. And in this case here, we don't have the distance between them, which would be FG or HD. But we do have a right angle triangle right in here, this right angle triangle, and we have the hypotenuse and one side. So by using Pythagoras, we can say that the square FG squared is equal to FE, the hypotenuse, squared minus GE squared. And FG obviously equals the square root of 61.22 squared minus 30.88 squared, and that equals 52.86. So then back down here, putting it into our formula for the area of a trapezium, which is FH plus ED divided by 2 times FG, the distance between them, equals 126.56 plus 95.68. I've worked out 95.68 down here for ED. It is simply AB minus GE, and it's 95.68. and we divide that by 2, multiplied by the distance between them, which was FG 52.86, and that gives us 5873.80 metres squared. All it remains now is to calculate the area of triangle BCD. Now there's two formulas for the area of a triangle. One is half the base times the height, but in this case here we neither have a base nor a height. However, there is an alternative calculation, and that is half BC sine A, or half the sum of two sides times the sine of the angle in between them, or the included angle. So we've got 46.5 here. So half BC times, in this case, CG times the sine of the angle between them, which is 108.2252. So we do that calculation, 0.5 times 46.5 times 46.5 times sine 108.2252. Remember that you must convert the degrees to decimal degrees and be using a calculator in the degree mode, and multiplying that out I get 1025.97 metres squared. So to work out the area of A, B, C, D, E, F, we add all of those together, 2885.19 plus 5873.80 plus 1025.97. We wanted the answer to the nearest 0.1 of a metre. That was required in the initial question, and that gives us 9755.0 metres squared. Okay, now that we know that we have AutoCAD available, let's see if we can just check out and see how things will go. So over here I've got the properties box. So just here we're going to click on the rectangle ABHF, and there we can see in the properties box that that's got an area of 2855.194, and here's our calculation just down here of 2855.19 down in this area here, as we can see. So let's have a look at our triangle. Here's our triangle here, BCD, and we can see down here in our calculations we've calculated the area of our triangle as 1025.97. Over here in the properties box we can see we've got 1025.954, so that's all pretty good. And then finally here we can just check on our trapezium FHDE, and we have calculated an area of 5873.80, and here over in our AutoCAD 5873.817. Just some slight little differences there, but nothing significantly. And then we can just turn on our total area and just check out our total area of the entire thing here, and we get a total area of 9754.94, and I've got 9755, so there's just a few little rounding errors and things there from our calculations perhaps, but nonetheless a reasonably solid check on the work that we have done. And just by a way of demonstrating how we can, if we can draw things, we can calculate them. If we can draw them in AutoCAD up in AutoCAD, we can check our calculations independently, and it's a really good way to go if the opportunity's there and there are important calculations that need to have a high confidence in them.